Imagine a single device with the power to wipe out an entire city in a matter of seconds. That's the atom bomb for you. Born amidst the chaos of World War II, this masterpiece of destruction changed the course of history forever. It was an unprecedented display of human ingenuity and the terrifying power of science. The United States, in a race against time, developed not one but two types of atomic bombs, Little Boy and Fat Man, each unique in design, yet equally devastating in effect. Little Boy, a sleek, gun-type design, relied on the fission properties of uranium-235. Fat Man, on the other hand, used plutonium-239 in an implosion-type design. Both bombs, though different, were united by a common purpose: to harness the power of the atom and unleash it in a catastrophic chain reaction. But what exactly gives these bombs their immense power? Let's dive into the science behind it. At the heart of these bombs, we find two isotopes: uranium-235 and plutonium-239. Their importance lies in their fission properties. You see, when the nucleus of either of these isotopes absorbs a neutron, it becomes unstable and splits, releasing a tremendous amount of energy. This process is known as nuclear fission. But for fission to happen in a way that results in an atomic explosion, there needs to be a critical mass of the fissionable material. That's the minimum amount needed to sustain a chain reaction. When a neutron from one atom's fission triggers fission in at least one other atom, that's a chain reaction. And in an atomic bomb, this happens almost instantaneously, resulting in a massive release of energy. Now, let's talk about uranium-235. This isotope of uranium is quite rare, making up only about 0.7% of naturally occurring uranium. The challenge was to find a way to separate enough U-235 from its more common sibling, U-238, and then enrich it. This process was both technologically challenging and resource-intensive during the days of the Manhattan Project. Plutonium-239, on the other hand, doesn't occur naturally. It's produced in a nuclear reactor when U-238 absorbs a neutron. This process was easier to control and scale up, making plutonium a viable option for atomic weaponry. These two isotopes, uranium-235 and plutonium-239, their unique properties and the scientific human endeavor to harness them, set the stage for the creation of the most destructive weapons in human history. Now that we know what fuels these bombs, let's look at how they're designed. The Little Boy and Fat Man bombs were not twins but rather two distinct designs, gun-type and implosion-type. Let's delve into the gun-type design, embodied by Little Boy. This design hinged on the isotope uranium-235, or U-235 for short. The concept was quite straightforward yet ingenious. Picture two subcritical pieces of U-235. One piece is stationary, like a target, and the other is fired towards it at high speed. This projection is much like a bullet from a gun, hence the name gun-type. When these two pieces come together, they form a supercritical mass. This rapid assembly ensured the U-235 didn't have a chance to undergo spontaneous fission, which would have disrupted the chain reaction needed for a successful detonation. Shifting gears, let's examine the implosion-type design, as seen in Fat Man. Unlike the gun-type, this design utilized plutonium-239, or Pu-239. Here the process is more complex, and the name gives a hint. The plutonium core is surrounded by a shell of conventional explosives. When these explosives are detonated, they generate a shock wave that compresses the plutonium inward. This implosion consolidates the plutonium into a supercritical mass, triggering a nuclear chain reaction. The precision required for this symmetrical implosion is part of what made this design so challenging, yet devastatingly effective. So, as we've seen, the science behind the atom bomb is a complex interplay of physics and chemistry. The gun-type and implosion-type designs each had their own unique approach to achieving a nuclear chain reaction, relying on the fission properties of different isotopes and the clever manipulation of these materials. Whether through the swift merging of two uranium masses or the intricate implosion of a plutonium core, these designs revolutionized warfare and marked a new era in human history. The atom bomb, a device of destruction, is actually a marvel of science. Its destructive power is undeniable, but it's the intricate science behind it that truly commands respect. Two isotopes, uranium-235 and plutonium-239, found themselves at the core of these weapons, chosen for their unique fission properties. Fission, the splitting of an atomic nucleus, releases an enormous amount of energy, but it requires a critical mass of these isotopes for a chain reaction to occur. In the heart of the Little Boy and Fat Man atomic bombs we find two different designs, the gun type and the implosion type. The gun-type design of Little Boy used uranium-235, swiftly combining two masses of this isotope to avoid spontaneous fission. On the other hand, Fat Man utilized an implosion-type design with plutonium-239, using conventional explosives to compress and consolidate the plutonium for detonation. And thus we unravel the science behind the atom bomb, a masterpiece of destruction, yet a marvel of scientific achievement.